My name is Justin Chow, and I'm going to be presenting RTDSP Project 3. So right here I have the instructions for RTDSP Project 3, and the next series of videos are going to be covering the different tasks for Project 3. So Project 3 is about designing FIR filters for certain applications. So in Project 2, we discussed how to code in C and like how many taps an FIR filter can be, how many taps an FIR filter can be used depending on the sampling frequency, and a bunch of those, and observe some of the effects, audio effects, through WinDSK. But now we're going to actually start coding some of those effects ourselves using the information we learned from Project 2. So the first application we're going to cover is the graphic equalizer. Now, we discussed the graphic equalizer in WinDSK, and the graphic equalizer is basically composed of a low-pass filter, band-pass filters, and then a high-pass filter at the end. So how this is going to be structured is similar to how we first designed our filters in MATLAB through simulation, and then brought it into C. We're going to start by working in MATLAB, and we're going to generate those coefficients in MATLAB, and then using that MATLAB function to turn those coefficients into a C file, we'll then be able to implement it in C using Code Composer Studio. So right now we are in MATLAB. I'm make sure I'm recording still. Okay. So this is the code that we have for the graphic equalizer. So the graphic equalizer, you first have to select which one of these frequencies to use, because these are the various frequency sampling frequencies of the DSP processor. Right now I've selected 1, which indicates a sampling frequency of 8,000. Now I've chosen the sampling frequency of 8,000 for 2 reasons. First of all, since it's the lowest frequency, it gives me the most number of taps, so that I can create the best FIR filter, so that way our graphic equalizer works properly. Secondly, since I'm only going to be using audible signals, I'm not going to be using any high frequency signals. I don't expect to use any frequency signals higher than 3 kilohertz. So having a sampling frequency of 8,000 should prove no problems in terms of aliasing due to high frequencies. So after selecting our sampling frequency, we can select the scaling factor. So how I've designed the graphic equalizers, there are set intervals down here which describe the different low pass, high pass, and band pass filters. So from here, the first interval is going to be from 0 to 500. And from 0 to 500, it takes the first scaling factor. So from 0 to 500, it'll have a scaling factor of 2, which makes it twice as loud. And the next interval right here is going to be from 5,000 to 2,000. It's going to use this next scaling factor, which has 1.25, and that's going to be for this range right here. And then depending on the sampling frequency, we're going to basically take this sampling frequency value and concatenate the corresponding Nyquist frequency at the end. So since my sampling frequency is 8,000, I'm going to take this 4,000 Nyquist sampling frequency and concatenate this to the end of my frequency interval. That way I can create a frequency interval from 2,000 to 4,000, which is my third interval, which will take this third coefficient, which is 0.1. So how I've had the coefficient set up right now is that these lower frequencies have a high coefficient because the lower tones are generally quieter, so I'm making them louder. These middle tones I've left almost the same at 1 because they're relatively moderate in volume. And for those high frequencies from 2,000 to 4,000, I've attenuated down to 0.1. And I've attenuated those high frequencies because those high frequencies tend to be high-pitched and kind of headache-inducing, so I want to remove those, let's say. So based on the sampling frequency as observed in Project 2, we have to choose the number of taps. So based on the sampling frequency, we can have a different number of taps. Now, if you remember the Project 2, and for the circular buffer, we could have up to 767. Like if I open up the coefficient generator, you can technically have up to 767 taps for the circular buffer. But I only put 751 just to be on the safe side. Even though I don't expect to perform any additional operations, I just chose to limit it to less than the absolute maximum just in case. So in here, this is where we're going to start concatenating those additional Nyquist frequencies on the end of our interval, depending on which sampling frequency we chose. So like if I chose 96,000, then it would concatenate 4,000 here, and then 4,000 to 6,000, 6,000 to 8,000, 8,000 to 12,000, 12,000 to 16,000, 16,000 to 24,000, and 24,000 to 48,000. But since I'm only doing 8,000, it's only going to concatenate the 4,000 to the end of this matrix to create 3 intervals from 0 to 500, 500 to 2,000, 2,000 to 4,000. All right, so now we have the extract response. This is going to be the number of taps. So this extract response is going to be the coefficients that we use in our FIR filter. And here we have the frequency response, the FIR frequency response, and the scaled response. These are vectors that are going to contain values that I'll discuss later. So the first thing on how we're going to design our graphic equalizers, we're basically going to design FIR filters. We're going to design an FIR filter, a low-pass FIR filter from 0 to 500, and then a band-pass filter from 500 to 2,000, and then we're going to design another high-pass filter from 2,000 up to the max Nyquist frequency of 4,000. So we're going to create 3 FIR filters, and then we're going to scale each of those FIR filters and add them together, and that's going to form our graphic equalizer. So this for loop is used to generate each FIR filter in the loop. So we're going to start here, and we develop the low and the high. And these are going to control which FIR filter. So for the first FIR filter, the low is going to be 0 to 500. Then in the next loop iteration, this will be 500 to 2,000. And then in the last interval, it'll be from 2,000 to 4,000. We then shape our frequency response based on our frequency intervals, and we plot them. Then we convert the frequency response into time response using the IFFT, and we window the frequency, or we window the time response to the number of taps. And then we will go ahead and we plot the time response, and we plot the windowed time response. And remember, this is being performed for each FIR filter generated. So the total number of figures gets quite large because we start with the first FIR filter here. This is its shaped frequency response, its time response, and then we windowed it to only include. So if you look at the bottom here, this is all the taps, all 4,000 taps. But then we're going to window it. So then we window it to only about 751 taps for the 8 kilohertz circular buffer. So then, as you see, the next one does the next filter, and then its time response, and then its windowed response, and then the last filter, its time response, and then its windowed time response. So then we generate the frequency response, and then we extract the time response. We extract the time response from the windowed response right here, and then we scale the time response based on the scaling factors for the gain. And then let me make sure I'm not outside this loop. So I want to make sure I'm staying inside this loop, which I need to. Yeah, so after we scale this is the end of the loop. And then we loop back into the next loop, or the next filter interval, which, like I said earlier, was going to be 500 to 2,000. Repeat this process. We shape the filter, take it to the time domain, window it, and extract it, and then we scale it. After we've created those different FIR filters, I went ahead and plot each of the FIR filters on top of each other just to see how they would look overlaid on top of each other. And that's what this response here looks like. So right here, we see that we have the filter, the low pass filter. Well, I need to run this code because that's outdated. Let me run this code one more time. So let me make sure I have it right. Yep, so there we go. When we run the code, I have the low pass filter at 2. I have the 500 to 2000 at around 1.25, and then I have the higher frequencies from 2000 to 4000 attenuated to 0.1. So this is all this loop does right here is just plot each of them overlaid on top of each other. And so the total response is literally just going to sum each of the scaled responses for the different FIR filters together. And so then I'll go ahead and plot that. So if I plot that, this is what the time response looks like when they're summed together. And this is what it looks like in the frequency domain. So in the frequency domain, you see it's just the combination of all of the filters together. So you see it goes 2, 1.25 to 0.1. So after I've gotten the scaled response, and I've summed up the scale response for all the FI filters to the total response, I use this total response as the coefficients for my FIR filter. And so this FIR dump to C is the script that converts these coefficients into a readable C file so I can use it in Code Composer. Now I also include this function down here, which is simulate. And this function down here is basically just supposed to just simulate the FIR filter, similar to how we did the simulation in Project 2, where we fed the input samples one at a time using the for loop. So if we look at the simulate function, the simulate function has fs, f1, f2, and f3. So how this works is it takes three sample frequencies and creates a composite signal right here. So it takes, this is f1, f2, and f3, three sinusoids, adds them together to create a composite signal. And then this line down here would technically overwrite this. And this creates Gaussian noise. So if I want to test for specific signals, I would comment this line out. That way I can test the composite signal. If I want to test Gaussian noise, I leave this line in here and then I can comment this one out because I won't be testing the composite signal anymore. So if I have it set up like this, I'm going to be using Gaussian noise generated by this random function. So then and this is the same as observed in Project 2. I feed the input into the first index, I do the dot product, and I sum it together. And then I take the exit, and then I take the output, and then I shift. This is shifting the buffer right here. And then at the end, after I've calculated for all the time intervals, so for all n samples, I'll have the excitation, which is just the input, and I'll have the output, which is the response, and then I can plot them and observe them right here. So what that does look like is, since I have it set up with the Gaussian noise right now, the excitation just looks like Gaussian noise, so it just looks random right now. And its frequency spectrum right there technically contains all frequencies. But when I look at the frequency response after the filter, you can see the general shape of my bandpass filter, or my graphic equalizer based on, so if I overlay this, or if I grab this one, see they have a similar shape because the graphic equalizer will basically shape the Gaussian noise into the shape of the filter. And then down here, this is the same function used to convert the coefficients into a C file. So this is the file location, and this is all the same as before. So if I'm going to run this for 8,000, since, like I said, I don't plan on using frequencies higher than 4,000 because those are hard to hear and are high-pitched. So I ran the simulation, so I should have updated coefficients. So we can now go into Code Composer and see those coefficients. So this is the graphic equalizer project. Now the FIR interrupt service routine. The ISR, like before, is where all the main code is located. But notice how the code in here is very limited. It has the coefficient H header, just like before, and it still has all this normal stuff, and it's based on the circular buffer code. So notice this is exactly the same as the circular buffer code because we're just implementing an FIR filter. So there's no need for any additional operations. This is the exact same FIR circular buffer code that was observed in Project 2. The only difference is the coefficient. So if I open up the coefficient header, you see we have 751 coefficients, and here's the list of all 750 coefficients. I check my DSP configure head and make sure it's set to 8 kilohertz to match the sample frequency we used in MATLAB. From here, I can go ahead and run it. So I run this. All right, good to go. All right, so the first thing we're going to test is a lower tone. So the first, if just as a quick refresher, the first interval ranges from 0 to 500. So anything less than 500 hertz should have a gain of about 2. So if I take a lower tone, such as a 300 hertz signal, and I output it, notice how this is the tone for the 300. Sounds kind of quiet, but lower tones are generally quiet. So next, I can take a higher tone signal, a higher frequency signal, such as a 1000, and if I put it here, the gain should be about 1. If I put this 1000 hertz signal, I need to close out of the other signals. So what I use, a 300 hertz signal. That's what a 300 hertz signal looks like. I use the 1000 hertz signal. Notice how right now even the 1000 hertz signal sounds kind of quiet. And that's because if I turn up the volume here, but then go back to the lower tone will sound louder. So this is 2 times the original volume. And then I go to 1000, which is approximately the normal volume. And then I need to go to a higher frequency. So the last frequency range is between 2000 and 4000. So I'm going to grab a 3000 tone and play it. And notice how the tone is very quiet. I'll turn up the volume here. So this is turning up the volume very loud so that you can actually hear it, but I can also turn the volume back down. So this is the 3000 tone. And if you compare it to what the 1000 tone sounds at this level, this is the 1000 tone. And the 300 tone, which will be amplified, sounds very loud at this volume setting. So the graphic equalizer will definitely boost up those lower tones to be a lot louder. It'll leave the medium frequency tones about the same, and it will attenuate those higher frequency tones. Now the graphic equalizer can be adjusted for different values here to make them louder or softer. So if I wanted to decrease the lower tones to say 1.5, and let's say I increase the upper tones by 2.25. I'm hesitant to increase the higher tones too much because then they'll become loud and cause headaches, but I'll increase it to 0.5. So if I run the graphic equalizer again with these new values, so this is what the shape of the filter roughly looks like with Gaussian noise shaping it, but specifically it'll look like this. So notice how we have the medium tones that are louder than the lower tones, but I still kept the high tones attenuated because I don't like having high-pitched noises very much. So notice how when I put Gaussian noise, it's shaped to match the shape of the filter approximately. And my coefficients in here should be updated. So let's go ahead and run this. Alrighty. So if we take our lower tones, this is our lower tones. And if we take our higher tones, or our medium tones, these are our higher tones. And if we take our highest tones, notice how now, since I've increased the gain on the higher tones, that the higher tones are now more prominent. So this is what the graphic equalizer does. I've only tested, or in this demonstration, I only tested the graphic equalizer at 8,000 kilohertz sampling frequency, or 8 kilohertz sampling frequency, because I don't want to use higher test samples because then the high frequency noise, the high pitches can get irritating. So I've left it, but the same idea applies. The only thing that changes is that I basically add more of these cutoff frequencies to the end of the interval, and then I have to change more of these coefficients. So right now, since I'm only using 3 intervals, only the first 3 scaling factors are actually used. So notice that I can leave the rest of these to be whatever values I want, and they won't be affected unless I grab higher sampling frequency. But then in order to do that, in order to test that, I would need to use higher frequency tones, which I don't want to use because those high frequency noises are irritating. But, and the same idea applies also here. When I increase the sampling frequency, the number of taps decreases. So even if I wanted to use higher frequency or a higher sampling frequency for a larger range from a graphic equalizer, the filters themselves would be less accurate because I would have less taps. And that's pretty much all there is to the graphic equalizer. The graphic equalizer is essentially just a bunch of filters, a bunch of low pass and band pass filters that are scaled and added together.